we've waited long enough. Everybody's eager to get started. So Spencer, do you want to go ahead and kick us off?
Yes, sir. Thanks a lot, Mr. Jake Lynch. I'm Spencer. I'm from the Spearbit team. We also got Alex Baragzasi, Jake Lang from Spearbit, and then the man himself, Brock from Nascent. Quick administrative note, wanted to welcome everyone to this Foundry seminar co-hosted by both Spearbit and Nascent. And then a quick note for the future, we're going to be having more of these seminars. So please give us some feedback about the types of topics you'd like to see in the future. So Jake Lynch, back to you. Thanks.
Sounds good. So the format for this, the agenda is in the invite. I'm going to hand it over to Brock, and Brock will stop intermittently to answer questions as they come in. So make sure you guys, if you have any questions, to drop them in the Q&A. And without further ado, it's all yours, Brock.
Thanks, guys. Hi, everyone. Just want to say thanks to the Spearbit team and everyone for coming out. I'm going to be dropping a link in the chat that just has a few things here for us, and I'll go ahead and share my screen. Just get us started here. I guess for a quick intro, my name is Brock. I am the chief architect at Nascent. We are a crypto fund, so we invest in early stage projects as well as incubate our own projects, and we like to think of ourselves as builders. So I do a lot of building myself, and part of that is Foundry. So I'm a contributor to Foundry. And a lot of the features we'll see today, I implemented myself. And so if you have any questions about how things work, feel free to ask those as well. But without further ado, just a quick agenda here. I'm going to be talking about what is Foundry and why it's so cool. Going to help you get set up quickly. And then we're going to dive into writing some code and writing tests and fuzzing and all the cool features of Foundry. So just briefly, so what is Foundry? Foundry, to quote our marketing materials, is a blazing fast, portable, and modular toolkit for Ethereum application development, and it's written in Rust. It basically has two core utilities. The first is something called Forge, and the second is called Cast. And so Forge, which is what we'll mostly be working with today, is all around smart contract testing. Right now, that is limited to Solidity, but we have contributors that are currently working on implementing Yule, so you'd be able to write Yule contracts, as well as work going for Viper. And it's very similar to DAppTools. It originally started as a fork of DAppTools, at least conceptually. And the other kind of comparable products are Truffle and Hardhat. And then on the other side of Forge is Cast. Cast is quoted as a Swiss Army knife of utilities. So it has things like API decoding and encoding and interacting with chains and that sort of thing. So why should you guys care in the first place about Foundry? You guys have Hardhat, and I just want to take a moment and back up and think about any language you guys have written in. Did you write your tests in another language? I think it's quite strange that we have an industry where you not only have to be an expert in Solidity, but also JavaScript. And that really is bad for the developers as well as security in the long run. Because if you expect to master a language, how can you master that language if you have to spend half your time developing in another language just to test core functionality of your contracts? Yeah, all the homies hate JS. Exactly. Big number is the bane of my existence, and a large reason why I'm so adamant about why writing tests in Solidity is so important. And one of the major reasons why Foundry exists is because DAppTools kind of led this developer experience charge of writing tests in Solidity, but it's written in Haskell and it's just kind of slow. And so Foundry is very fast. And on top of that, when you're writing in Solidity, you actually have lower context switching. So if I'm writing in Solidity and then I go and write a test, that there's a cost associated with writing that test in JavaScript because you have to switch your brain to thinking in JavaScript. And so you actually lose time and lose productivity by going over to JavaScript. And so being able to stay in Solidity, it can speed you up. And as you see, like there are significant speed ups relative to DAppTools and also Hardhat for that matter. There's benchmarks out there as well, and we're only getting faster. So we're in the process. Foundry is under active development. We're going to be switching out our EVM backend to a new backend, which will be about 50% faster. So you'll be surprised at how fast a lot of Foundry is already, but it's only going to get faster. And just to briefly cover some of the cool features, obviously fast. Two is what's called mainnet forking, which is basically where you provide an RPC endpoint and you can rely on mainnet state. So if you want to interact with existing protocols, if you want to interact with DAI, WETH, etc., you have the ability to fall back to a mainnet contract or a testnet contract, whatever has an RPC available and is EVM compatible. We also have something called cheat codes. So cheat codes, we'll dive into this a little bit more later, but cheat codes allow you to modify the EVM state explicitly. So whether that's changing the message sender or transaction origin or block time, block height, or doing more complicated things like expecting a revert in a contract and those sorts of things. Cheat codes are very powerful. And then we also have a debugger. So some of you may have used either the Truffle debugger or the DAppTools debugger. Foundry ships with a debugger as well, which you'll see a little bit later. We also have traces. So again, like DAppTools, we record all of the calls that occur during a transaction, and we can display that in a very nice way and ABI decode all of the inputs, and you'll see that later. We also have fuzzing. A lot of what I want to talk about today is about fuzzing and the importance of fuzzing and how to get started with it. We also ship with multi-compiler version support. So if you have a contract, you can use any compiler version. We'll be generating a repo along the way here. A finished repo will be available after the talk. But with that, let's sort of hop in. You're welcome to follow along, and I'll be taking questions if anyone has any as we go. But first off, like just installing Foundry is very easy. All you have to do is copy this URL and paste it, and you'll be able to install Foundry Up. Foundry Up is the version management for Foundry and Forge. And so if you just run Foundry Up after the curl, then you'll have Foundry installed. And so then you can run this command here. And with that, I'm going to switch my screens. Okay, you guys should see my desktop here. So to begin, let's just let's just create a repo. So Forge init is sort of like a create React app type command. Yes, I can make it bigger. And can people actually see?
I can see it.
Great. Awesome. So Forge init creates a directory for you and populates it with with a structure that is used in Forge. And let's just go ahead and run that. You see that we installed something along the way and initialized a Forge project. So let's go ahead and CD into there. And let's just go ahead and open this up into a text editor. And I assume you guys can see this. So we have 2 folders, lib and source. I'm sorry, I can't make the folder size any larger here, but we have lib, which is where your dependencies live. You have source, which is where your main contracts live. And if we check out lib, we see there's DS tests in there. We'll cover that later. We have a git ignore, a git modules. Yes, Ivan, by the way, for anyone who is on Mac OS, you have to have a dependency called libusb installed. You can homebrew it. If you go to the GitHub page for Foundry, you'll be able to see the command in there. I'm pasting the link for the actual repo, and it's in the chat. And we also have this foundry.toml. This is a configuration file where we can define certain aspects of our tests. Right now, it's relatively limited, but at its core, we have a source, which is kind of where your contracts live. Oh, I want to mention before we dive too deep, if you are coming from a hard hat project, most hard hat projects are compatible. You'll have to do a little configuring. I would recommend hopping into the Telegram and seeing how other people have done it. But in theory, you should be able to use a hard hat repo with Foundry. And so like for hard hat, this would instead be contracts. But we use source. And then out is just an out folder, libs. So this is where your dependencies live. And then this concept of remappings. Remappings is basically just helpers so that you don't have to mention the complete source. You can say, all right, DS test, like it's always in lib, DS test, source, like those are where the contracts live. Okay, so that kind of covers the structure. We have in source, we have a testing contract, which we'll cover, and we have the real contract. I want to make sure people can see fine. Sounds like some people are having issues, and I'm sorry for that, but great. So as we go, you know, a lot of times when you're developing, you know you're going to need some dependencies. And so first thing we're going to do is we're going to forge install what's called the Forge standard library. And so that's just Forge ships with the ability to do some dependency management. It's not a full package manager, but effectively, if I run this, we can see, okay, it installed. And if we check our lib, it's now in our lib folder. Great. And additionally, I am a Soulmate stan, so we're going to go ahead and add Soulmate as well, because I am a gas optimizer, and so is T11. So we're off to a great start. Now, let's build a contract that allows people to deposit and flash loan the tokens inside of it. And so I'm just going to paste a little bit of a starter for us here. And basically, we're going to be using 8.12. We're going to import ERC20, a reentrancy guard from Soulmate. And we have a contract called Flash Loaner that inherits the reentrancy. We're going to have a token that is flash loanable, and we're going to do some internal accounting with pool balance. And so and we're also going to have an arrow. So we want to make sure that in our constructor that no one's going to be creating this with address 0, accidentally screw that up. Great. So we have a little bit of a contract here. Let's go ahead and I like to, in general, as I write a contract, write a test alongside of it. So let's go ahead and get our testing set up. So here's the base contract here. I'm actually just going to go ahead and show you kind of how this works. So we have a contract test and which inherits DS test. DS test comes from DAP-Hub, and it has a few helper functions. And so this is kind of the default test setup. And we have this test function set up, and this is basically a before each block. So if you're coming from JavaScript, if you were writing a test, you'd have before each. And then every test is a public function that starts with the word test. And so if we just run this right now, it's just a forge test, and we see it's done, we passed, and we get a little report here, and it tells us how much gas we use. And so that's how you run a quick test in Foundry, and Forge is just Forge test. So now let's expand, and we started our contract here. Let's make sure that, all right, if we do pass address 0, I like to, anytime there's a revert, make sure that that revert is we're actually able to hit that revert in an expected manner. So for this, it's just token address equals address 0. So I am going to do a little bit more setup first. So I'm just going to paste some things in here. And so what we have here is we're still importing the DS test. We're importing from Forge standard. So we added this as a dependency, and then we're adding a mock ERC20 from Soulmate, as well as the contract at the top level there, our flash loan contract, right? And so a lot of this is the same, right? We have our setup contract, and then we have some state things. And I want to touch on this VM. So this is the cheat codes contract. It's the same as DAppTools HEVM address. And this HEVM address is in DS test, so you don't have to ever remember it or anything. But this is basically a contract that is sort of exists within Foundry. And so it allows you to access the EVM internals and do some interesting things. It's where you can access the cheat codes. We're also going to instantiate some users. So Alice and Bob, Lee and Lidor. We're going to define a mock ERC20, and we're going to define our flash loan. And so in setup, what we want to do is we basically want to, all right, we're going to, we'll touch on label a little bit later as to why I use this. It doesn't change anything from a contract perspective. It's just a utility for traces, which we'll see in a bit. So we label, okay, Alice is Alice, Bob is Bob, address this is the test contract. We create a new token and we label it, and then we go ahead and create the loaner, and then we mint ourselves this contract some tokens. But now let's go ahead and write a test. Just going to head. And so what we want to test is we want to make sure that this address 0 cannot be 0. So again, we start every test with a test, the test word, and then this can be anything. So I like to name mine what I expected. So in the constructor, non-zero token reverts. And so this VM expect revert, we expect the call with an address 0 to revert. And so we're telling the VM, hey, the next call, we are going to expect to revert with this token address cannot be 0 selected. And so if we go ahead and run that, Forge test, we can see it passes. So it did indeed revert with that error. Awesome. So let's start to build out this. People will need to be able to deposit into our flash loan contract. So we're going to, let's add another error, which basically says, yeah, if you can't deposit 0 tokens. That doesn't make any sense. So let's catch that and revert. And then we transfer it from the user, and we do some internal accounting and add the deposit amount. Additionally, we want to, just be overprotective and say this is non-reentrant. So no reentrancies. And so again, let's actually instantiate our loaner with some tokens. Let's start it with 100 tokens. So we do the approve and deposit. Great. Now let's just go ahead and make sure that this works as expected. So I'm gonna add another test here. This is testing that we're doing the internal accounting correctly and making sure things line up. I do want to point out, we'll actually get to that. So we do the approve, we deposit one token, and then we make sure, hey, the pool balance is 101. That's our internal accounting. And we also ensure that the token balance is equal to the pool balance. And so this assert equal basically just does a comparison between the two. And so then if we go ahead and run a forage test, we can see, oh, sorry, forgot to save. We can see, yep, okay, it passes, great. Awesome, so we're on our way to having a secure contract. I'm gonna take 1 second to read some questions here. Why do you use revert instead of require? So with custom errors, you have to, if you have a custom error, you can't do require yet. You're required to do a revert for it. It's a little bit of a semantic thing with Solidity. Okay, and with that test, great. Now let's add a check to make sure that we revert when we deposit 0. So again, we're going to add a new test with a good name. We're going to expect revert must deposit 1 token minimum, and then we're going to deposit 0. And so again, we expect this to revert. Let's go ahead and give that a test, and it does. Awesome. But maybe you're wondering, like, okay, what is this actually doing? This is where I'm going to introduce traces. Traces allow you to see kind of what is happening. And so here, all we're doing is this VVVV is basically just telling, hey, I want this output from forge test to be more verbose. And so 3 will give you the output for failed tests, 4 will give you for passing tests, and 5 will give the setup as well, which we'll see in a second. And then this M is saying, hey, I want to only run this test deposit non-revert amount. And so if we run this, great. We get this output. It only ran this one test. We can see, okay, it called the test itself. Then we called expect revert. And then with these bytes, which is equal to the selector of this. And then we see that we tried to call deposit tokens and it reverted with this and the test passed. And so notably on this expect revert is it doesn't halt the execution. So I could again do this and execution would continue on as you would expect. Sorry, I don't have tokens, so that was a bad example. But the second call did take place. And so you can do multiple expect reverts in a single test. Awesome. And I also want to point out the setup, right? So we do a lot of stuff in the setup. And so let's just go ahead and run with 5 V's, which is increasing the verbosity even further. And if we run this, okay, now this trace is a lot larger. I'll spread this out here. And now we can kind of see what this label does. And so what it does is it says, it labels a particular address so that anytime it shows up in a trace, it says, okay, like when we called test token mint, it replaces the address with the named contract. So instead of having to remember, okay, B4C is the test contract, I can go ahead and label it. And you can see, okay, we passed in 10 times the 18 for the mint, and we got the transfer event that was emitted from address 0 to the test contract. And so the traces are incredible for figuring out what is happening in your contracts. And they help you debug and all these things. And so I just wanted to take a moment to kind of point out this functionality for you guys. And now if we continue on, let's go ahead back into our flash loan contract and let's actually add the flash loaning ability. And so we're going to add a good number of errors and the actual functionality here. So we have 3 errors here. Must borrow at least 1, not enough tokens in pool, flash loan has not been paid back. And so we define our function that takes how much the message sender wants to borrow, and we add non-reentrant just for some safety. We do a check. Okay, we should probably add a test for that. We do this, we check how much we have at the beginning in terms of balance before. We make sure that we have enough tokens in the pool. And also we want to make sure that our accounting, our internal accounting matches the current value of our tokens. And then what we're going to do is we're going to go ahead and start the flash loan process. So we're going to go transfer the message sender our balance, the borrow amount. And then we're going to let them have this function called receive tokens. And so I'm just going to create an interface for that real quick. And so we're going to be calling the message sender with this function. They're going to do whatever they want with the tokens. And then afterwards, we're going to make sure that they sent at least what they gave us back, right? So we do balance after. We make sure the balance after is not before the balance before. If it is, then we revert with flash loan has not been paid back. And I'm going to stop and look through some questions here and make sure that there's nothing super relevant. Can you configure the compiler output selection in foundry.toml? Yes, you can. If you run forge config, this outputs all of the functional flags, config flags. And if somewhere in here you can specify the Solidity version. I actually don't see it right now, but you can. Is there a way to measure test coverage? Not yet. It's a work in progress, and we'll touch on some of the things that are being worked on in the future of Foundry going forward, but not quite yet. One of the nice things about HH tests is you can do nested state transitions by nested before each. What approach do you recommend for doing this in Forge? Example, start at 0 state, do some tests, including one that shows we can deposit, then do a batch of tests that start from having funds deposited, etc. So we're adding something called table tests, which I think sort of get to what you are. Okay, sorry, I'll save this for later. Okay, let's head back into the contract. Great, so we did our flash loan. We're gonna do the function and make sure that they paid back. So let's write some tests for this. I'm gonna go ahead and add the receiver. So we had that iReceiver, and so it just takes a receive token, the token address, and the amount. We're not actually going to use this amount for now because we want to be able to specify how much we're sending back, because this contract can do whatever it wants once it has the tokens. But we need to make sure that we have a parameter for that. And additionally, I'm going to add, I'm going to inherit this in our test contract. And let's begin by making sure that if we try and borrow 0, we get an error. And so that's this. And as we go along, okay, we got to keep this in mind. That's sort of an invariant, which we'll touch on in a bit. And we also need to make sure that the token, let's make a function to make sure that we get, we hit this code path. So borrow more revert. So if we try and flash loan to the 250th, there's no chance that that contract has that many tokens. So we expect that to revert with not enough tokens in the pool. And one more time, let's just go ahead and say, we're not going to return any. We want to make sure that we hit this code path. No one can steal tokens from this contract. So those are the reverting test cases. And now let's finally add a test case where we think everything should be passed. And so we're going to set the return amount to 100, and we're going to borrow 100. So when we flash loan, we'll return the 100. And then we want to just make sure that the loaner pool balance is 100, so nothing changed in the internal accounting, and the token balance of the loaner is equal to the pool balance. So let's just go ahead and run a forge test. And great, everything passed. So it feels like we almost basically have a totally secure contract. It doesn't seem like anything really can get messed up at this point. But I do want to take one moment and talk about some of the cheat codes that are available to you, right? This is a very simple contract where, there's very little state. There's an immutable and a pool balance. But a lot of contracts you'll come into contact with have, owners and other state, right? And so access control is a very challenging thing to test a lot of times. So let's kind of mock that up and say, okay, we're going to have an owner state, and we're going to have some modifier that only the owner can call. And for simplicity, let's also just go ahead in the constructor. Let's add that whoever created this contract is the owner. And so now we have this state with a modifier. Let's go and add a function like update owner. So only the owner is allowed to change the owner. That makes sense. And just for some example purposes, let's go ahead and add this echo sender. And all it does is just return the message sender. And we're going to be using this to kind of showcase a very powerful aspect of cheat codes. And so now what we're going to do is we want to make sure that only the owner can update the owner. Only the owner can change the owner. And so what we're going to do is we're going to use a cheat called start prank. And what this does is it says, hey, instead of this test contract being the message sender, let's make Bob the message sender. Additionally, if we wanted to change the origin, you could also do like that. It's overloaded such that you can change both the message sender, which is the first parameter, and transaction.origin. But since Bob is not the owner, we expect this code path to be hit if Bob is indeed the owner, or sorry, if Bob is indeed the message sender. And so let's go ahead and try and make Bob in the context of Bob being the message sender, the owner, by calling update owner. And for good measure, let's echo the sender as well. And then we're going to call stop prank. This tells the VM, hey, switch back to this contract as being the message sender. So if we run forge test, the match test only owner. And this uses regex. So all you have to do is get a little bit of the test name and press enter. And you can see, yes, okay, indeed, the test passed. We called it, we started the prank. Then we expected a revert. So when we called update owner with this, with Bob being the new owner, we got a revert saying not owner. So indeed, even though the test contract was the one that created the flash loaner, we were able to switch the message sender to Bob. And we can see that here, echo sender, yes, Bob indeed was returned as the message sender, and we stopped the prank. Great. So I just wanted to take a minute to showcase sort of this will be a common workflow for a lot of people to impersonate other accounts. It's called prank because it's a prank call, right? It's a little play on words there. And a quick answer to console log, yes, you can. So if I come in here and import console.sol, I don't remember the console address off the top of my head, but you could do console log like you do in hard hat. So it's compatible with hard hat console log. Why do you need to pass Bob into start prank? So this start prank, it takes an address of which you want to set as message sender. So I could do address 0x01, and now the message sender would be 0x01. Does that make sense? And so the reason we do Bob is for that reason. And yes, so start prank is for when you're doing multiple calls. And so since we have this update owner and then echo sender, we want to be able to do multiple calls. And so this is a full, hey, prank with the message sender as Bob until I tell you to stop doing so. You additionally have just prank, which if I ran this, this echo sender would just output the test contract. And so that's the difference between prank and start prank, is whether or not you want it to be long-lived. And so in this case, this stop prank would not be necessary. You could just do this. And yeah, again, you can see the result there. Great. That's sort of the a little taste of cheat codes. We'll touch on some more, but I want to start to dive into, is our contract secure and how do we know? One of the most important things that I hope you all take away from this is the importance of fuzz testing. And so we're going to start getting to fuzz testing and why they are so important. I generally find fuzz tests find more bugs in contracts than anything like this, where you're testing explicit code paths and this and that, because the way fuzzing works is you define, okay, I want some random input, and basically what Foundry does for you is it generates that input, and then you can pass that along to your functions. And so I'll just write a quick function here for testing our deposit. So in general, again, like to have at least one fuzz test per function in my contract. So for this, right, let's take a look at deposit tokens. So we're gonna fuzz test deposit tokens and make sure this pool balance never gets out of whack with the transfer from and that sort of thing. And so we're going to again define a test, and then I like to distinguish fuzz tests, and so a lot of times I'll put fuzz right after the test, and then sort of more context later. And you pass in you can define as many random inputs as you would like, and you make it a public function. And so what this will do is Foundry will generate a random input here. We'll mint some tokens so that we have enough for whatever we're doing. And then we're going to approve the loaner for that amount. We're going to check the pre-balance. So before we do any actions, right, we record the balance of the loaner, and then we're going to deposit that amount. And afterwards, we're going to write our asserts. So in our case, we want to make sure that the pool balance is equal to whatever tokens were in there before, plus whatever we deposited. Additionally, we want to make sure, again, that our token balance of the loaner is equal to the pool balance. We want to make sure our invariant that we have in there stays solid. And so now, if I run this, matching on the fuzz deposit, we can go ahead and run that. Oh, we got an arithmetic overflow underflow. So this is because we're using 0.812, we have both safe math introduced in 0.8, and we also have compiler generated panics. And so we automatically decode compiler generated panics to human readable. So arithmetic over / underflow, the compiler generates that for you when you're doing safe math. And so here it looks like, oops, when we minted, we actually minted too much and we had an overflow in our mint amount. So let's go ahead and add one more cheat code in here. It's called vm.assume. Basically what this says is it tells the compiler, it's okay if you do this. It tells Forge, it's okay if you pass an input too large, just continue on to the next fuzz run. And so I want to also quickly point out, we have this runs 215. So this is ran 215 times with a whole bunch of random inputs. And we found an error in our
in this case, in our test, not in the actual contract yet. So this VM assume fixes that. It basically just makes it so that whatever our amount is, we can't overflow in total supply. And so we'll be able to mint okay. So if we rerun this with our new thing, oops, we also forgot deposit. And so all we have to do is vm.assume amount greater than 0. Awesome. So if we again run this one more time with our assumes, then we see it passed. Awesome. So we know for a fact that given the random inputs we provided, that the internal accounting is correct and the token balances are as we expect. And you note that we only ran 256 times. Foundry is very fast. So in our config, we can actually up that, 10,000 runs. And if we wait a second, 10,000 may have been a little aggressive, but there we go. Now we know that if we random 10,000 inputs, we're good. And so that adds to your sense of security inside of in your contract. And I'm going to do a quick test or quick check if anyone has any relevant questions here. So what types are supported with fuzzing? All types are supported with fuzzing. And we'll touch on some of the smart things we do. I've been saying random, but not everything is totally random with these inputs. We try and get a little bit smarter with that. Can you configure the fuzz test input distribution, or is it just uniform or the demand of the input parameters? So right now you cannot configure the input distribution. There are people smarter than I that have determined sort of what are good input biases. And a lot of that does come from the libraries we lean on. Okay, anything else relevant to fuzzing? When fuzzing, do the sample inputs adjust to the param type? Yes. So if you have a uint 128 instead of a uint 256, we will generate a uint 128, not a full uint 256. Does it become a fuzz test because of function prefix, or is it just because it has arguments? It's strictly just because it has arguments. I like to denote in my function name, in my test names, that it is a fuzz test, just to easily distinguish. So I can do forage test and test fuzz, and all of my fuzz tests would run. And so that's kind of the rationale I have there. There's other rationale, like if you know that, like, for example, transfer fun, and you want to have matching function names, that is also a good pattern to use. It just comes down to personal preference. Can you vary the number of fuzz runs by function contract? Not currently. We will be able to eventually add, we're planning to add like vm.fuzz runs as a cheat code, and then you'll be able to specify, okay, I want this run 10,000 times, because I think it's very important that this function is tested, or this test is slow, and so I only want it to run a few times. So that is coming. And again, to answer the VM assume just tells the fuzzer, if you encounter a random input like amount, if you pass it a Boolean, like type uint 256 max minus amount is greater than the token total supply, just go ahead and return and continue on, go to the next run, right? So instead of 256 runs, it would really be 255 with some assumes. If one of those inputs, if this evaluated to true. Okay, I think that covers a lot of the questions right now for fuzzing. I want to keep moving forward here. All right, great. So we have we fuzzed a deposit, and we saw how to use assume. Now let's go down to our flash loan and start fuzzing our flash loan.
So we come in here and we have a test here. So we're going to take two input variables. One is the amount we want to borrow, and one is how much we want to return. And so as you recall up here, we have our return amount, which basically just tells this contract, okay, when we receive tokens and we want to transfer back, let's use the return amount. And so we're going to fuzz that, and we're going to flash on with the borrow amount, and then we're going to make sure that our assertions hold, right? So we have that invariant in here where we want to make sure this is always true. So let's go ahead and try this out. And we are going to see some errors here. And I won't belabor this point, but again, we can see we have to do the borrow amount is greater than 0 because we hit that code path. And so we add that, and that would fix that error. I'm also just going to go ahead and add some other ones in here, and I'll briefly touch on them. So we also need to make sure that we have the amount of tokens that we want to return. If we don't, then we won't be able to do that transfer. That transfer would fail. We also need to make sure that the BR amount is less than, because as we have a test up here, we know that if we don't return at least the amount we borrowed, then it's going to fail. And so basically you want a test, a fuzzing test, to try never to revert. You want it to not revert in any case. Otherwise you get all of this garbage. And so the last one is we want to make sure that the loaner actually has the amount we want to borrow. Okay, great. So now I think this is a very good fuzz test. Let's go ahead and run it again. Uh-oh, our assertion failed. So this assertion down here failed. And this is why fuzzing is so important, is because all of a sudden we can see, okay, the expected value for the loan pool balance was supposed to be equal to the token balance. Sorry, the internal accounting was supposed to equal to the token balance. But as we see right here, that's not the case. And if we look in here, actually, that's a pretty big issue, because if that's not the case, then this contract is no longer usable and all of the funds are frozen in there. And so this fuzz test has surfaced the fact that we have a bug in our contract. We use a strict assertion when in reality, this shouldn't be, this should never occur. And so if we're thinking about this, really what we just need to do is, all right, we already checked that they're returning more. Why don't we just do pool balance is equal to balance after? And all of a sudden we've fixed our bug, and this contract is truly unstoppable, and you can't freeze funds. So if we run it again, I still have 10,000 runs on. Down to 1,000 runs. We can see, okay, now it passes. Now we can be pretty sure that this is working as expected. And I just want to take this moment. I'm going to comment this out and sort of highlight the issue here, right? So if I do this, and you know, as you hit this, it'll output. Okay. Sorry, let me real quick run this one more time. So we see here contract flash loan fuzz. So we passed a 1 and a 2, and that resulted in some weird state. So this 2, as we see, is the return amount, and the 1 is the borrow amount. So what I like to do is when I encounter one of these, is I like to go ahead and make an explicit test for it. That generally will mean that, like, as you make more changes to your code later, you'll be able to ensure that you don't have that same error. And so broken flash loan, the return amount was 2, the flash loan was 1. And let's just go ahead and add this assert. And so now, if we do this, oh yeah, sorry, this explicitly, we took out the fix, but this explicitly shows that is broken. So if we add this back in and run it again, great. Now we have a test case
in addition to our fuzz test, to cover this surfaced issue. And I also want to, one more time, I'm sorry, I know this is a little confusing. I want to take this point to showcase the debugger. So if I run this command, so Forge has this command called run. And basically what it is it runs a single function for you. And you provide a path, a target contract. In our case, that's -t contract test, and provide a signature of the function we want to call. And so test broken flash loan is what we want to see, and we want to add debug. And so I'm going to expand this out and go ahead and run. And now we're in what's called the debugger. And so I just want to give a quick overview of what's going on in this. At the top left here, we have the current program counter. And basically what that is what's actually going to be executed at the next step of the EVM. And this can be a fantastic tool for understanding what's happening at a lower level. And so this has Vim binding, so J for down, K for up, etc. You can see all the commands, the movement commands down here. And so J goes down, K goes back up. And so at the top right, we have the stack. And so this push 180, we can see, okay, the first item at the top of the stack has this 80, and then it pushes a 4 and so on and so forth. And we have the temp store. And so down here, sorry, given how big this is, we have our memory layout. And this can be a little hard to understand if you don't know what you're looking at, but it showcases what Solidity is and the EVM is doing internally with its memory. And at the bottom left here, we have the actual source code that's being executed. So right now, all of this is highlighted. Basically what that means is we're doing some setup that isn't specifically tied to a certain line of code. It's just general contract behavior. And so we can step through, step back up. We can press S to go to the next jump destination that was executed, S, and we finally see a call. And then you can still go into the next call, right? And so this goes into a different contract. This is now in the actual flash loaner contract. And you can also press C and capital C to go to the next call. So I'm just going to keep moving forward because our revert was kind of towards the end. So I'm just keep pressing C, keep pressing C. Right now you can see we're about to, or we just returned from the receive tokens function. And so I'm just going to now go to the jumps. We're going to check the value, the balance of this address. It's a static call. Again, I'm just going to step forward. Okay. And so now I just want to point out one thing here. So up here, you can see the stack, and we are comparing balance after is less than balance before. That's what this less than opcode is. And if we look at the stack, we see 65 and 64. 64 is 100 in hex, 65 is 101 in hex. And so we're looking at this and we see, oh, balance after is 65 and balance before is 64. Sorry, balance after 65, balance before is 64. That's explicitly what happened when we sent more back than we were expected to. And so this is actually why this showcases, oh, this actually broke the pool balance equals balance before thing, because effectively balance after here should be equal to balance before if we wanted to only allow people to return exactly what they borrowed. But based on this, we actually are just checking if balance after is greater than or equal to balance before. And so we have a strict comparison with a non-strict comparison, equality, excuse me. Great, and so I just wanted to take a moment to kind of showcase some of the power of the debugger and some interesting things with it. I'm going to look to see if there's any questions around the debugger right now. Otherwise, I will continue on and touch a little bit on sort of where we're going with some of the Foundry stuff, as well as if we have some time, diving a little deeper into some of the fun cheat codes that we have. So there's a question here, can you use the debugger on a forked mainnet test to get opcodes for deployed contracts? Yes, you can. Right now, we don't support, so this is the source view in this bottom left corner. We don't currently reach out to Etherscan to ask for the contract code, but that is in the works and likely will be added within a few weeks or so. So you'll be able to have a run, a forge run command that would potentially interact with mainnet state. And if you don't have the contract source locally, it'll go out and reach for that, and you'll get a step-by-step view of what's happening. How to add a breakpoint. So currently we don't support breakpoints. We have looked into it, but not too deeply. We would like to add that at some point, but currently not available. Let's see. What is the difference between run and match? Match is purely a command line argument for testing. Run is if you want to do a proof of concept for an exploit or mimic a transaction, that's what run is for. It's for running one specific function. And this debugger right now, the CLI is a little bit of a pain to use. We plan on fixing that up and making a better experience for users, more similar to DAppTools if you've used DAppTools. Let's see. Okay, do you usually spend more time on the debugger understanding EVM internals or actual debugging? It depends. I would generally, I'll use it for very complex things. So anytime there's an exploit, a lot of times what I'll do is I will break this out and step by step trying to understand what is happening. It's very good for that. And it's also an incredible learning tool for EVM internals. You really get a sense of what does the Solidity compiler do for you? What does it not do for you? It's incredible for understanding how all of this works at a deep technical level to be a better Solidity programmer. And that's a large motivation for what we're doing at Foundry, is trying to make the community better at Solidity so that we have safer smart contracts. Will the debugger will have support for real-time value attached to the variables of the contract? Yeah, so I've seen this done. It's a little complicated. We would like to add that. I just haven't had time. You know, the debugger is in a state where it's useful and can be used, but there are improvements there. But right now, only a small number of users use it, and so if demand picks up for it, then it could definitely shift priority some, so that we have more time dedicated to developing features for it. Awesome. Okay, I think that answers enough questions about the debugger right now. I'm going to press Q to quit. Clear the screen. Okay, now what I want to do is I want to kind of give a sneak peek at what's coming down the pike for Foundry and how it's going to improve even the existing fuzzing infrastructure further to help you write even more secure contracts. And so a lot of the first thing I'm going to touch on is invariance, right? So anytime you have an assert in your contracts, generally what that is it's some sort of invariant. And a lot of requires are also invariants. It's basically you expect a certain case to never happen, right? So you expect the sum of balances to never be less than or greater than the total supply, right? You expect the sum of balances to always be equal the total supply. Now, there are reasons that may not be the case, but in most ERC20s, that is an invariant that you expect. And so kind of to showcase this, what I'm going to go ahead and do is I'm going to go create a new file here. And we're just going to call this feature preview.sol. And so I'm going to paste this in. So this is a very, very simple contract. Just going to delete that. We have two variables, flag 0, flag 1. They're both set to true at construction. And we have two functions, set 0 and set 1. And they each take an int and return a bool. So this should be return flag 0. And this should be return flag 1. And you can see, okay, if some weird condition hits, value is modulo 100, meaning it's a factor of 100 is equal to 0, then we're going to set flag 0 to false. And then set 1, if it's mod 10 equals 0 and flag 0 has been set, then flag 1 would be set to false. And so I'm going to go ahead and create a new contract for this. Let me paste this in. Sorry. Great. Let me just save this file. And so sort of an invariant would be like, okay, this is like some complex construction where like maybe it's a little contrived, but you could imagine a scenario where this is some deep in your code path where you would expect that flag 1 could never be set, right? That's kind of the idea here is that, or sorry, you would never believe it could be set to false. And so as you can see, this actually takes multiple steps to reach the case where flag 1 is equal to false. But let's for a quick second assume that we believe that flag 1 can never be set to false. And so we write a test, and this is an upcoming feature. It doesn't exist currently. So if you write something that says invariant, this is like the test flag, where if you set an invariant function, then it'll be run similar to a test. We'll touch on that. But it's not in the master branch right now. I'm going to be running it off of a branch I've been working on. And so our assumption is that flag 1 can never be set. So to test that, all we have to do is, or what you will be able to do is, this is a build of my branch with Forge, and I'm running tests, and I'm matching on the invariant. So I only want to test this right now. And so what this is going to do is going to try really hard to show that my invariant doesn't hold. And so I'm requiring that flag 1 is always equal to true. And we know, because this is easy for a human to know, yes, this can be set to false. But right now it's set to true. And so it has to set 0, hit this flag to set to false. And then it has to do a random input for this as well. And so it relies on a lot of the same fuzzing infrastructure that we had before. But what it does is it automates a whole bunch of calls to every contract that you have out there that has mutable functions. So what it'll do is it'll pick random functions that can mutate state, and then it'll provide random inputs for those. And it'll just call like up to, I think I have my current branch configured to 30 calls. And so it'll just try a whole bunch of things to prove that flag 1 can be set to false. And notice here, basically, if this function reverts, that means our invariant failed and flag 1 can be set to false. So it's very simple, but let's give this a go. So we run this. Oh, looks like it failed. So as you can see here, it tries a whole bunch of things. It tries set 0 with this big long number, yada, yada, yada. You can see here, set 0. Oh, this actually set the flag 0 to false. And as we continue, it goes along, and then, oh, it found one for set 1. As you see, if you mod that by 10, it equals 0, and we already set flag 0. And so our invariant shows that this invariant that it's never false is actually incorrect. And so on this point, you could imagine in our other contract here that we could have set this as an invariant that pool balance is always equal to balance before. This is a little complicated because it requires a secondary call, and you would need some function there, but I'm planning on adding some utilities to the Forge standard library that will help improve some of the functionality on that front to make it so that it's easier to surface these things to the invariant checker. And so I hope you guys understand why this is so cool. Yeah, I'm gonna quickly check if there's any questions here. I don't see any, so I'm going to continue on. But if you have questions, let me know. Add them to the Q&A. But you can. Yes. Okay. So let's continue on to some of the other things we're adding to Foundry, which is an even better fuzzer. I didn't touch on quite how the fuzzer works per se in terms of how it picks values, but we do some slight biasing. So we'll do the low values and the high values for a type, right? So we'll do 0, 1, 2, 3, etc., and then we'll do 2 to the 256 minus 1, minus 2, minus 3, etc. And that gets you a decent ways, but it doesn't get you everywhere. And so for this next part, I'm going to kind of showcase where we're going with the fuzzer. Excuse me. Okay. So we have two contracts here. We're going to import the VM.sol again, and we have this state owner. So this is a very simple contract. It just has an owner. You construct it with the owner, and then we have this function only owner, and require message that sender is equal to owner. Otherwise, it reverts with not owner. It's extremely simple. Not too much to see there. I'm going to comment this out real quick. And so in our testing contract, we initialize the contract, and we give it an address of 1234 1234. This is a totally random address for a fuzzer to choose, right? There's no real way it would ever be able to pick this randomly out of a hat. And so what we do, or what's coming up, is we actually do what we call EVM state lifting. So what that means is we look at the entire state of the EVM that has been instantiated, right? So we deployed a contract, we set its owner to this address, we have HEVM address as the VM, we have the test contract itself, and there could be logs and this and that. What we do is we take all of that and lift it up into a an array of values that we use as a strategy into the fuzzer. And so it's going to most likely with your contracts, you're more likely to have a bug around something that's in the state of another contract, right? So the address or this contract over here has some owner, and if you did this, that, and that, and you passed in this owner to this fuzz test over here, it may end up breaking it. And most likely that informed value is going to be better than just randomly throwing values at it. So for example, if we didn't have this, if I were to run this fuzz test on master, this wouldn't ever get caught. But since we do this state lifting, as we call it, we can show that this test is actually going to fail. So we expect revert not owner, right? So we're going to be calling this function, and we always expect that the message sender is never owner. We do a simple prank saying this random input is now the message center, and then we call only over. And so if I go ahead and do that, and again, I'm using a special build of Forge that will, there's a PR open right now for it. And run this, we can see we did indeed generate this 1234 address as an input to the test, which should surprise you, except that I told you what was going to happen. So we're working towards more intelligent fuzzing, and this is one of those cases. The next case, which I think is like a little mind-blowing, in addition to lifting state, we also we do bytecode lifting. And so what that means is, if you recall in the debugger, we had like push1 0x80, right? And we push that onto the stack. So what we do is we're actually adding all of those push bytes into the state dictionary, the array, right? And so we're more likely to pull random values that appear in contracts, even if they're hard coded. You don't have to write it to state and whatnot. So for this example, this is actually from Soulmate tests. We can see that there's like some complicated thing. And what we want to do is with both these tests, we want to prove that the fuzzer is smart enough to find this weird edge case. And so most of the time, we're just going to return unless we're very specific about our input. And that's kind of what makes a fuzzer better than others, is it's able to get specific about inputs. And we want to hit the case where this code path passes and we revert. And so to do that, we have to know, okay, 32 is in there. That's an important value, all of these bytes, and also this bytes 1. And so without this bytecode lifting into the state dictionary, the likelihood that we're going to generate some random set of bytes to make this fail is very low. But let's see if we can do that. And there we go. We happen to generate this 1. And to show it's totally not a fluke, I can change this to 91 and run it again. Oh. Okay, it does work, I promise. Sorry, that one was bad, but I did test it with a lot of values. Just that's one of the things about fuzzing actually that I want to mention, is in general, the longer you run it, the more secure you can feel about your contracts. But it is random values at its core, and so no matter what, it's more of a counterfactual where just because fuzz tests pass and invariant tests pass doesn't mean that it's exactly correct, right? So I see a question about symbolic execution and these sorts of things. So we currently don't dive into sort of proofs that your code does exactly what you expect, like the formal verification aspect. It's on our roadmap. We are working on a symbolic EVM as well that will help with that. But sort of the goal on a lot of this is to make it a very good experience from the user's perspective, to be able to make tests and test easily. Okay, so that was a lot. I want to make sure we have about. I want to make sure we get through some questions, and I don't want to overload everyone. I think we covered a lot of really good ground. We covered, what are cheat codes, how to use the debugger, how to use traces, and how to use the fuzzer, and where we're going forward. And I think I'm going to answer some questions now. I know technically this is supposed to go till 5, but it's a lot of effort here. So I want to answer questions, and if we also want to dive deeper into any of the Forge standard library. That stuff is really, really cool. I didn't get to touch on it, but I have a Medium or a Mirror post that goes into giving yourself $1 billion by explicitly modifying external storage state. So you just provide it with a function selector like balance of, and the standard library will write the token balance for you. So it would basically just be standard store, or really it's actually just tip now, like the address of the token, who you want it to go to, address this, and 2018. And this would give you 10 to the 18 tokens, which is really cool. And there are some limitations around it, but there's a lot of depth in the standard library as well as the cheat codes that honestly could probably use their own seminar. But I didn't want to, I wanted to focus on sort of the core of what makes Foundry cool today. So now I'm going to jump into some questions. So I didn't explicitly go over mainnet tests. I can do that if people want me to. It's pretty much you just do forge test fork URL, and if you have anything like ERC20 die is equal to address and then 0x whatever, then you could, and if you do this, you would be able to access the state of die by also adding this fork URL, which basically says, hey, use this RPC endpoint as the state for the EVM. Great. So now I'm gonna dive deeper into some of these questions. Okay. Why is there a difference between the sum of gas per operation and the stack trace versus total gas use? Yes, that's a good point. So, I also, sorry, there's one, I'll come back to that. The reason is for when you are doing gas optimizations, we remove the static gas cost. So that's the 21,000 base transaction fee plus basically 64 from the call data. And the reason we do that is purely because it lets the developer know what they can affect, right? So you don't always have to be doing the math in your head. Okay, I got to subtract 21,064 every single time. And so when you see like on a Forge test run, you see like this gas here, this is minus that static gas cost. Okay. Is there a way to test for reentrancy? Sort of. I mean, you can just do, it'll probably be in Forge standard for the invariant tests and that sort of thing. I still have to figure out a good UX for that. Is setup called again before each test? Yes. It's basically before each block. What's the difference between initializing things inside setup compared to outside constructor? So the primary difference is that in setup, it's really what you want to show for what you want to kind of show in your traces. So a lot of times the setup is ran every single time, and unless it's failing, you don't really want to see it. And so that's kind of the main, it's primarily a UX thing. You could never have a setup. Setup is totally optional, and you can do it all in line inside the test. So I can move this over here and then remove it, that sort of thing. Can you do console logging tests? Yes, answered already. Why do you need a pass bot? Answered. Dismiss. Is there a difference between using Forge standard VM.sol and using cheat codes interface like in the docs? There is none. The only difference is I maintain Forge standard VM.sol, and so basically, if you want to like upgrade your dependencies, so a new thing comes out and you want to just push that requirements like add the new features and whatever, all you have to do is do forge update, and it goes and grabs all the most recent commits from your dependencies, if that makes sense. Is there a special difference between assert and assert equal? Yes. So let's hop into DS test. So DS test is where you get the assert equal. And it's extremely overloaded and this sort of thing, but it emits these logs that say error A is not equal, or A equals B not satisfied for an address, the expected, and then the actual. And notably, it has this fail parameter as well that helps us understand what exactly failed in your contract. And so that comes up in traces. Yeah. Okay. All types, even arrays and structs with arrays. I believe that's for fuzzing. And yes, there are some limitations on structs, for arrays. But in terms of the length, for memory reasons, we limit it, I think, to arrays of max length 256. Instead of picking a num of tests to run, can you configure a time to run per test? Currently, no, but especially once we have invariant tests, I want to add that so that you can just be like, okay, I'm going to run this for 8 hours overnight and let it rip, and just to improve your security to find weird bugs in edge cases. So we want to add that. Currently, do not have it. Can I share my rice? Yes, I can. It'll be, I think it's already on my GitHub, but I'll make sure it's updated. Also, can we chain tests together so that the state changes persist as each test is chained? I believe you're asking, can I do like, not necessarily that, but if I come back over to this one, like this, and then this, and then this, or whatever, you can, but most likely the way that would work, it would be function global test public, and you would just call test flash loan, etc. test only, yeah, etc. So that's generally how it works. I think with table tests, that'll be more up your alley for that kind of functionality. Yeah. Let's see. Is there a way to create a more complex monkey test? For example, to test that orders in call does not break the contract. So I believe what you're referencing is like, all right, there are 10 different there are 10 different functions, and you just wanted to sort of randomly assign the functions. So yes, the invariant tests sort of handle some of that for you. But in addition to even help invariant tests, you can write different things. And I'll probably do a post about this once we release invariant tests. But you could certainly do some function that takes some random variables, and then if randvar mod 5, and you have 5 different functions that you want to call func1, et cetera, et cetera. So there's a little bit of boilerplate there, but it can be done. 1,000 fuzzing runs are per parameter, right? Two parameters mean 2K rounds. Is that right? No. So when I do 1,000 fuzz runs, that is generate 1,000 of parameter A, 1,000 of parameter B, but do it in one function call. So I'll pick a random value for A, a random value for B, and I'll then call the function. So like here, if I run this for 1,000 runs, then I'm only doing 1,000 calls to test fuzz flash loan, but there will be 1,000 different borrow amounts, 1,000 different return amounts. Do the 1,000 runs include the ones skipped by VM assume? Yes, but there is a you'll see in here max local rejects and max global rejects. So it is you can set bounds to make sure that you don't assume too many. And if you hit local is for a particular test, global is like for all of your tests. So you can make sure that you're being productive and have some safe bounds on that front. Can you go over again how return amount works? Does return amount always equal to the return of the next call? What if the func returns multiple values? So the return amount is explicitly just for when we take a flash loan, how much of that token are we going to get back? So it's just a state variable in the contract that we set via fuzzing, and then once we receive the tokens, then we reference the state variable for the amount we transfer back to the message sender. Can you explain again how you know which variables map to what position on the stack? Yeah, so that is a decent question. So there are, I just kind of knew based on, I had stepped through the function before. And so I knew, okay, I just watched for, right, this was the returned value. And then I tracked that from the response from the call and down into the less than check. So it's mostly manual tracking at this point. Again, referenced this before, where we'll likely add that at some point where it just knows, okay, this is the variable, or this stack item represents this variable, but that's a little complicated, so we haven't done it yet. How does the Foundry fuzzer in your last tweet tweeted example of this? I read that it uses different state values as input for the functions. Yep, I answered that. When symbolic execution for invariance? Sometime. Not particularly soon. We have other priorities. Yeah. Speaking of priorities, I do want to mention right now, one of the hassles of Foundry is deploying. There's a command called forge create. We also have forge verify. So after you deploy, you can verify your contract on Etherscan. Those commands are being reworked. We're going to have a forge deploy command. And effectively what that's going to look like is it will be something like contract deployment. And we'll have function stage 1 public. And we'll have a cheat code called vm.broadcast. And what this is going to do, and then we can do like add, ERC 20 token equals new ERC 20. Vm.stop broadcast. So what this is going to do, and we could do something like other.get name, name. So let's just give it 18. So what this would do is you would run this with a fork URL. It would say, it would do this get name just locally. So it would call out and simulate that function. And it could be mainnet state, it could be local state or whatever. And then with this broadcast, what it's basically going to do is it's going to create the transaction like you're going to send it off to mainnet. And we will record, it'll start recording all the transactions until you call stop broadcast. And so then you'll have this like array of transactions that you want to set. And so what this is it's a deployment system that you get to write in Solidity. You don't have to go out into JavaScript and use complicated things. It's like, Solidity, so you should be able to write your deployments in Solidity. And so this will all create these transactions, and then you'll be able to, it'll have like state management. So at what stage you are, so you have like a stage 2, that you do some other thing and so on and so forth. And so that's where we're going with the deployment. I already, I've implemented the broadcast functionality, but I kind of got nerd sniped into doing fuzzing things. And so I'm going to need this feature soon. And so that's a lot of this, a lot of the motivation for me is like, I need these features, so I'm going to go implement that. And if any of you know Rust or want to start learning Rust, I encourage you to do the same, where it's like, I think this feature is awesome. We're very welcoming to PRs, and we try and help out contributors getting familiar with the code. And so this is where we're going with the deployment side of things, which I'm very excited for. Okay, how does the randomness work for choosing which functions call for the test of an invariant? So the choice of functions is it's probably uniform. I would have to go back and look. It's still in the process of changing, but I believe it's uniform over the total set of functions. It first uses a contract to call, so it's uniform over a set of contracts, and then it's uniform over a set of functions, such that if those functions are state mutating, it won't call like a view function or constant or something like that. By defining some variables, it could be possible to influence the fuzzer and guide it to do the fuzzing. Is that right? Yes. And we plan to add even more things where you'll be able to give hints to the fuzzer about interesting parameters in your contract. So if this Bob thing, this would likely be picked up, but that's sort of what assume does already. Like imagine assume on steroids and like different parameters you can tweak. That's likely going to be where we land on that, is more cheat codes that allow you to parameterize the fuzzing. And so you also have in the state lifting branch, you can also define like how much you want to weight using random variables versus state variables. We'll probably add that as a cheat code, so you can be like, all right, for this test, state won't matter. I just want random values. For other ones, it'll be like state is the only thing that's going to really matter for this. That's less likely, but yeah. When is this feature released? So this state dictionary will probably be released in the next few days. There's some performance things that I've been working through. We got to keep tests fast. Yeah, so soon. Invariant tests, probably a couple weeks. Maybe, hopefully shorter than that. We'll see. What does testing locally with deployed contracts? Is it any different to how we would do it locally when we import other contracts? So really, you just have to define interfaces and the address that they live at and provide the fork URL. So I've used it for governance actions. So if anyone's used Compound Governor Alpha or Bravo or any things like that, it's super easy to test governance things. So it's as simple as tip the token, and then you can do propose, and then you can VM.roll, which increases the block height or block.number plus like 1600 or whatever it is. And then you can do execute, right? So it's extremely easy to be able to do this thing, to mock up tests for deployed contracts. And I recommend it for governance proposals specifically. Is there any reason you do an early return instead of a VM.assume in that bytes example? Does return waste a run? There's really no difference. The reason you would use assume is just so that in this example down here, right? Like this won't revert if there's a bad input. Use assume when like it may revert, and you want to make it easier on yourself to say, all right, this can't be less than 10 and it can't be greater than 1,000. Then And if it is, then it'll revert. It's basically use assume to make your test less complicated. I think you misread my question earlier about output selection. I meant to ask how would you configure the output fields in the contract artifacts? Yes. I actually haven't used that, but there's an extra outputs config option someplace. I don't remember where exactly, but yeah. Oh, yeah. So check the documentation. There's a really good resource. There's a lot of good resources in awesome Foundry, GitHub, as well as the main README. I forgot to do this. I wanted to do this. This is cool. So this is what's called a gas report. So if I run gas report, ignore the failing thing. But what this is it's a summary of all the function calls and how much gas they use. And so it's better than this sort of setup where you get to see, okay, for my flash loaner contract, deposit tokens was called 12 times. The minimum was 596. That's probably in the revert case. On average, it costs 33,000, median 39,000, the max 39,000 as well. So most often 39,000 seems to be reasonable. Echo sender, flash loan. And so this also gives you a sense of, oh, I'm not calling some function. And you get this, it's not coverage by any means, but it at least gives you a sense of sort of what you have covered, as well as it may be indicative of what people are most likely to use as well, based on your testing, or the more complex the function. We also have deployment costs. This is in gas, and then deployment size. So this is in bytes. So you can manage and track. Okay, if I come in here and set the compiler, what is it? Compiler runs, optimizer runs. Yeah, optimizer runs. So if I come in here, optimizer runs, and I set this to 1 million, save it, and rerun the gas report, we can see, okay, the deployment size went up a bunch. We went from 436 to, we had 500 bytes, and we could see how this changed. Soon we'll have an export, so it'll just create like a .gas report, and so then you'll be able to track it across Git commits and track how you're changing your gas usage. Okay. When testing contracts with only owner, would you typically let the test contract be the owner, or prank to deploy from a specific address? It really comes down to your needs. I've found most of the time I want the test contract to be the owner, and then when I explicitly want to test from a user's perspective, I'll use prank. But it comes down to your own preferences. I think I answered this one. Return amount. Can I go a bit deeper into the debugger? I can a little bit. There's a few functions. There's A and S, which goes to the previous or the next jump destination. You have J and K, which goes up and down an opcode. You have C and capital C to go to the next call. And those are the primary navigation things. You can also do like 10J or 10K, and that'll move 10 opcodes up or down. I hope that helps. I can also potentially do more of a tutorial at some point, but not right now. I use MacBook Pro, and ForgeUp always takes at least 5 minutes with ForgeBin and CastBin. Is there a way to make it faster? Yes. So ForgeUp is sort of deprecated. Now you should use FoundryUp. So ForgeUp was when everyone would build from source. We now release binaries, and so downloading and upgrading. So if I run FoundryUp, which again, it's linked in, I'll drop this link one more time for everyone. That has the install instructions at the bottom, but if I run this, you can see it just downloads and we're done. And so that just downloaded the newest version of Foundry, which generally we release every single night with a bunch of bug fixes and feature pushes. And so some people have been set up a cron job because we ship pretty much a few PRs a day. It's slowed down a little bit as we've gotten to a decent level. Is it legit to call tests within other tests? Yeah, it's totally fine. In general, I think it's better to use a fuzz test if you're trying to get complex state transitions, or an invariant test, as we'll soon have. But yeah, it's generally fine, and you can have helper functions and call other internal functions within a test. I do it all the time. How do you envision Foundry looking in 1 year from now? Hopefully, we're the top Solidity testing framework, and maybe just outright top framework in every EVM compatible language. And I think we'll probably, we almost already have the best fuzzer. There are things that we find that Echidna doesn't even find. I would still say Echidna is probably better for right now, but like we are close on the heels and we're just getting started. And so I think we'll probably have the best fuzzing. We'll probably have symbolic execution. We'll probably have the best deployment UX. We'll likely have symbolic execution and the best UX for that as well. Can you go over again? Wait, I have already answered this one. Return amount working in fuzzing. Can I do a quick example of expect emit? Yes, I will do a quick example. Well, so expect emit is another cheat code. So if I had some event T that UN256 indexed a UN256B. So an expect emit, basically it takes 4 parameters, all Booleans. So what this is indexed var 0, indexed var 2, indexed var 3. And then data. So basically the way events work is they have topics. Topic 0 is always the SHA-256, or sorry, KECAC-256 of the, it's like the event signature. Topic 1, sorry, this is topic 1, is the first index parameter, and the second one would be the second index parameter. And then finally, events work by just pushing all the data out, ABI encoded, or I think ABI encoding, and pushing it into the data slot of an event. And so what expect emit does is it has true, false, false, true. This means check that index A matches what I'm about to emit. So let me just T1, 1. And then if I called some function f dot emits T. So what this does is it tests that emits T actually does emit the event T. So that should be emit. And so the way this works is you pass what you want to actually check against. So if I don't care about this number 1, I can set this to false. If I don't care about this indexed number 1, I can set this to false. And since we only have 1 index parameters, these 2 don't matter. And so we emit the event here. It records it and says, okay, I'm looking for the next call to emit event T with, I don't care about any index parameters, but the data should be equal to 1. And so then it would check, it would call this function, f emits T, and make sure that f does, or emits T actually does emit T with whatever parameters you specified. Is there a way to get gas calculations just around a single line of code, even if the test has many lines of code? Currently, no. Your best bet is to hop into the debugger. We plan on adding, it's honestly pretty trivial to do a line-by-line evaluation of gas costs, but we currently don't have that. It'll probably be, it will leverage a lot of what the debugger already does, but expand that out into something more like the gas report. Is there a way to do gas snapshots between commits so that you know, or that you know of to show on GitHub Actions? I believe you're asking, is there a way to like check the diffs? Currently, once we add it'll be GRE gas report export. So you can also do gas report export, and that will create a .gas report file, which you can git commit and then track across commits. Coverage feature, it's not been worked on quite yet, really, but it'll leverage a lot of what we have in the debugger already. And so it's probably not that big of a lift. Just we want to make sure that we output a compatible standard. So there are standards for coverage reports, and that's just like an annoying overhead that we haven't undergone researching, so that it's compatible with all your GitHub Actions and that sort of thing. So when we start that, I would recommend everyone join the Foundry Telegram. It's linked at the top of that HackMD that I posted for updates on what's currently going on. Expect to make example, please, sir, already done. How can you run a test by sending a mainnet token to a test address? For example, can you send a test token address link at the start of a test? At the moment, doing an annoying hacking, importing Uniswapper. Yeah, so let's say I kind of covered this, but like with this die example, if I wanted to give myself die, imagine ERC20. Imagine 123412334 was the actual die address. What I can do is for this simple token, you can do tip address die address this on E18, and now you'll have die for this for all of your tests, right? And there are some limitations with tip. If it's a proxy contract, it currently won't work. I'll probably add it at some point, but I just haven't had the time. Also, you'll probably want to check Forge standard. I guess I can do that, but yeah. Tip. Yeah, so it's token, who you want to give tokens to and the amount you want to give. It's a set balance, not an add balance, just FYI. The wording is a little weird, but that's how you do that. In the debugger, you saw the values that caused the assert to fail were on your stack, but how did you know which variable mapped to which? I think I answered that, so I'm going to move on. When Foundry token? Probably never. How did I get started with smart contract development? I had a project. I wanted to do a yield aggregator back in 2019 before Wi-Fi and all these things, and so I had a goal, and I just used that goal as motivation to teach myself, and I heavily relied on Stack Overflow and understanding how transactions are built, and just built it up over time. It takes time, but if you have a motivating enough project that you find fun and enjoyable, then you'll make really good progress. Any recommendations on how to run complicated deployment pipelines until the new deployment features come out? Worth learning Forge Create or hard hat tasks. So Forge Create is, it's okay for like complex. It's not fantastic. You have to mix in, Forge with cast with bash. And so it's this big mess where you would write a bash script. And if you need a call out to existing state, then you would use cast to interact with the chain
and then you would do for it to create using the parameters from it. It's a big mess, which is why we're trying to move away from that system. But for the short term, I know a lot of people that are still using Hardhat for deployment. So you can definitely consider that. Can I do these once a month or every 2 weeks? Not 2 weeks. This is quite a bit of work. So yeah. But I will try to continue to put stuff out there to get people involved in this. And again, if anyone is interested in learning more about the contributing side of things, please join the Telegram and reach out. We definitely want more contributors. When did you decide to join Paradigm? I have not joined Paradigm, and I probably won't ever. I am at Nascent, and I love it. And I work with some awesome people, and I get to spend time with incredible portfolio companies like Spearbit. Mustard versus ketchup. Porque no la dos. Mustard, ketchup, and mayo on a burger, please. You said something about working on a symbolic EVM. Can you say more about that? What is the progress? Yeah, so there's a guy from Paradigm, coincidentally, who's been working with some people on a symbolic version. Without going into too much detail about what that looks like and when it'll be released, it's likely going to keep, it's probably going to take a while, to be quite honest. We're leaning on some very smart people for that, but until I get totally nerd sniped by it, like I got nerd sniped by the fuzzer, I don't know if a lot of progress we've made. There are now a couple of people that are working full-time on Foundry, but we would like to have people focus on making sure core functionality is there before going on a nerd sniped trip into symbolic EVM land.
All right, Brock, that was absolutely incredible. We want to thank you a ton for doing this for us. And then, so that everybody knows, make sure you check out the Discord link in the chat right now. You can join Spearbit and talk to a lot of people like Brock who are working on some cool things in the industry. We will be posting this video to our YouTube, so also check that out. And yeah, we can't thank you enough, Brock. Thank you.
Yeah. Thanks everyone for coming out. It's been really awesome. And thank you again to the Spearbit team. You guys rock.
Brock DAO coming out soon. All right. Bye, everybody.
Thanks, Brock.